we are looking at some examples of ideal gas law problems today. So, first off, let's talk about a tire. So, let's say we've got a bike tire, some sort of tire, and we are, well, actually, let's say maybe a car tire because I'm going to say, anyway, whatever, some sort of a tire. We're going to say that we are going to pump it up to 50 psi, which is not a standard unit, when the temperature outside is 90 degrees Fahrenheit. So let's say we're pumping up a tire when it's hot outside, or was hot outside, but now it's 40 degrees Fahrenheit. And what happens to the pressure? P nu is what? Okay, so let's use this to look at, or let's, well, first let's get it into the units that we need. So when we're doing the ideal gas law, remember we have PV equals nRT, and the P is in pascals, V is in meters cubed, and is moles, R has its own units, and then temperature is in Kelvin. So let's go ahead and convert these. And so, find my units here. So we could do pounds per square inch and do a bunch of conversion factors, but let's just use 6895 pascals is 1 psi. 1 pound per square inch. All right. And so if we've got 50 psi, so let's call it P1, I guess. Or P old. Anyway, we'll call it P1. P1 is 50 psi, and we have 1 psi, 6895 PA, pascals. And so 6895 times 50. All right, so we got 344.8 10 to the third PAs, kilopascals, if you want to go with that. Alrighty, and then we need our temperatures in the right units. So we want Kelvin actually, but let's get to Celsius first, as we're in Fahrenheit. So the formula to go from Fahrenheit to Celsius is the 5/9 of T Fahrenheit minus the 32 degrees. So let's, I guess we'll call it T1 since we call it P1. T1 is going to be 5/9 of when it was hot outside, 90 degrees minus 32 degrees. And so T1 is 5 times 90 minus 32, and then divided by 9. Okay. So we get 32.22 degrees Celsius, right? But we really want Kelvin, so temperature 1 in Kelvin, we have to add 273 temperature in Celsius plus 273.15. Probably 3 sig digs is enough for us, but let's go ahead and do that anyway. So we're going to add to this 273.15. So we get 305.4 kelvins. All right. And let's just go ahead and do the second temperature. So T, I guess we'll call it nu, is again needs to be converted from Fahrenheit to Celsius first, and that was 40 degrees minus 32 degrees. And so let's see, 5 times 40 minus 32 is 8 divided by 9, 4.44 Celsius. So add 273 Kelvin 277.6 Kelvin. Okay, so what can we, so we're going to use the ideal gas law, PV, P1, V1 equals N, well, I guess put ones on everything for now, T1, and we also have P nu, V nu, N nu, R, T nu. Okay, so what stays the same, what changes, what can we do? So R is a constant, it's going to stay the same, right, all the time. We're going to assume that the tires are, the air is in the tires, it can't escape, so N is going to stay the same. N1 and N nu are equal to each other. And we're also going to assume the tires are, full, they're blown up, they're not going to be changing size, so we're going to say the volumes stay the same as well. All right, so those three things are the same from here to here. So basically saying V1 is equal to V nu, N1 equals N nu, and R equals R. All right, so let's think of dividing these two equations by each other. So let's say divide this. So we divide both sides. So we're going to have P nu over V nu. I shouldn't probably have that. Think of dividing both sides. They're equal things. Divide by equal things. We have an equal thing. N nu R T nu. All right, so the N's cancel since they're equal. The R's cancel because they're equal. And the V's cancel because they're equal. So we end up with the equation P1 over P nu equals T1 over T nu. All right. And we're looking for P nu. So let's solve that for P nu. Bring that to this side. Multiply both sides by P nu. All right. So that goes away and P nu is over here. Bring these to the other side. So P nu is going to be P1. Flip this over and multiply. So T nu is going to be on the top over T1. And so that becomes, let's see, 344.8 kilopascals times the new temperature. This has to be Kelvin. So T nu is 277.6 and the old was 305.4. So P nu is 344.8 times 313 kilopascals, which isn't really very helpful when you're pumping up your car tires to wonder what if you're at a good pounds per square inch kind of number or not. So let's look at this a little bit. So since we're using this ratio, right, P over P kind of thing, it really doesn't matter what units we're using because the conversion factors are just multipliers and they will just cancel out. So we could also just say P nu and just do everything PSI. So we could use the original 50 PSI, and then the temperatures are in the same units, so they do matter because they're not just a linear scale. We've got all this complicated formula, so we can't do this with the temperatures, but we can with the pressure because it's just a multiplier. So 277.6, 305.4 still need to be Kelvin, but we can then get the new pressure this way. So let's just do 50 times 277.6, 305.4. So we get 45.4 psi is P nu. And you've probably seen that your tires seem flatter in the cold weather. You usually have to pump them up again. I've had cars that start sounding the alarm saying I have low tires when it suddenly cools off after it's been hot, and you had your tires at good pressure when it was hot. So hopefully that's an example that makes sense to you. All right, so let's look at another example here. Let me get a different marker. This one's not too happy. All right. Okay, so let's just look at calculating the density of air. All right, so we'll say air is made of I don't know if that's easy to see or not. Let me get a different marker here. Air is primarily made of nitrogen. All right. Looked up, Googled it. Air is 78% nitrogen, N2 gas, and 21% O2 gas, and that oxygen number stays. It's amazingly fixed and amazingly what we need, right? We get in trouble if we get much different than that. And so that's 99%, and then there's 1% of a mix of other gases. But for this problem, let's just go ahead and use 79% N2 and 21% O2 just to have 100% numbers here, and go with that. So we're going to say this is our composition of our air, and we want to know what is the density of air. And we need a temperature and a location. So density of air at 20 degrees Celsius and at sea level. All right, so let's calculate this with the ideal gas law. All right, so ideal gas law, PV equals nRT. So let's see, what do we know? Well, we can use sea level to tell us. That's kind of where we define atmospheric pressure. 1 atmosphere, or normal atmospheric pressure, is at sea level, and so we'll say that the pressure is 1 atmosphere, which is 101.3 kilopascals. So we use that to get P. We've got T in Celsius is 20 degrees Celsius. So that means T is add 273.15. So that's 293.15 if we want to get detailed there. Kelvin. All right, so we've got T, we've got P. We're looking for density. So it's probably we're gonna use this to calculate V. R is a constant. N. All right, so we're gonna assume we have a certain amount of the material to deal with, a certain amount of air, and figure out its density. And so we'll probably just say N equals 1 mole. Check my notes. I think that's what we want to do here. Just to just find the density of 1 mole of air will be the same as the density of 20 moles of air. It's a uniform thing. So let's just find the density of 1 mole to make the problem nice. Okay, so we need to get the mass. If we say we have 1 mole, right, we need to know what is the mass to get the density. So density is mass over volume. Okay, so we've got, if we're doing, okay, so it looks like we've got everything we need to go ahead and get volume, and then we also need to use moles and that kind of information to get mass. So I guess let's go ahead and get volume here to start with. And so we can use the ideal gas law, rearrange to get V is going to be nRT over P. We said we're going to have just 1 mole. R is 8.314. What are the units on R again? Joules per mole Kelvin. All right. T is right there, 293.15 Kelvin. Divided by pressure, 101.3 kilo. So let's just write it as 10 to the third, just so we don't forget it. Pascals. So now all of our units are standard. And so then the volume, let's plug that in. Alrighty. So we get 0.02406. We'll keep it extra sig dig just for now. Cubic meters. Okay, standard unit for volume is cubic meters, and everything else was in standard units, so we should be good. We had 1 mole here, cancel out the moles, so forth. All right. All right, so we should be good on units. Okay, so we got volume. Now we need mass. All right, so how do we get mass when we got moles? We need the molar mass, right? But we've got a mix. We got a mix of, we've got air, which is a mix of nitrogen and oxygen. And so we'll use these percentages then with the molar masses of those elements to get a molar mass average kind of a number. So we're going to take 79%, which is as a fraction, or as a decimal, 0.79 times the molar mass, well, I'll just write it out, molar mass of N2 plus 21%, or 0.21 times the molar mass of O2. All right, so that's going to be 0.79, and then nitrogen is 14, and so N2 is 28 grams per mole, and oxygen is, or O2 then, oxygen 16, O2 would be 32 grams per mole. All right, so let's plug that in there, plug those numbers in. You still see that? I think we can. So we've got molar mass of air, at least by our approximation here. Let's get these numbers. 0.79 times 28 plus 0.21 times 32. And we get 28.84 watts, grams per mole. And we probably, to use this in terms of finding mass and things, we really want it in kilograms. So let's say that's 0.02884 kilograms per mole. Doing a conversion factor, right? 1,000 grams is 1 gram. 1,000 grams is 1 kilogram. Okay, so that's MA of air. And so we want mass of air. All right, and so we said we had one, well, so in general, mass is the number of moles times MA, which is mass per 1 mole, right? And so we have 1 mole times 0.02884 kilograms per mole. All right, so the moles cancel, and so that's just how many kilograms we have. So since we only have one, we got 0.02, only 1 mole. It gives us a mass of, that's equals in number to our molar mass. All right, so we've got everything to get the density of air then. So the density of our version of air anyway is mass over volume, 0.02884 kilograms, divided by our volume, which was 0.02406 cubic meters. Okay, so we get 1.199 kilograms per cubic meter. So we don't really need so many sig figs, so let's say 1.2, I guess 1.20 kilogram per cubic meter. Okay, so density of air is close to the numbers we've used in the past, so it looks good. All right. What would happen to this problem if the temperature was different? Let's go back and see what happens if the temperature is a lot hotter. Let's say it was 40 degrees Celsius. What would happen? All right. Well, just kind of looking through the process. Where do we use temperature? Well, first we had to convert it to Kelvin. And so it would change so we used the temperature to calculate the volume. And so if we think about it, when we have a higher temperature, the volume is going to be higher, right? The molecules get excited, they move about more, and so they spread out, and so the volume of the 1 mole spreads out, and so we would have a higher volume, right? And then that volume gets used in here. This was mass over volume. Right, so we have less density then, right? So if this number got bigger, then the density would be smaller. All right, hopefully that makes sense. It's thinner air when it's moving around, spread it out, we'll get less density. Okay. Let's see. Let's look at another example here of a, let's see how to do this. Let's look at a hot air balloon example. All right, so there's some assumptions and approximations here, but we can just get some ideas. So say we have a hot air balloon that is the balloon before it's blown up, and the load, the basket and the ropes and the person or whatever, all the things that the balloon is going to carry. Let's say the mass of the balloon, let's just call it 200 kilograms. All right. And let's say the balloon, when it's blown up, has a volume of the balloon is, it's just, again, just not real sure how realistic these numbers are. Found some stuff on the internet, but let's say 300 cubic meters for the volume of the hot air balloon. All right, and so we want to know, let's see, what are we looking for? We want to know how hot, what is the temperature of the hot air need to be to float this balloon. Okay, we probably need some assumptions here in terms of pressure and things like this. So let's just go ahead and say that we're at atmospheric pressure, we're at sea level, so we're going to say that pressure is just 1 atmosphere, which will be 101.3 kilopascals like we had before. And are there other assumptions we need? We'll just use our density of air number that we just calculated. Come down here. Well, I can't get it to come down. We'll just use the density of air number that we had before for 20 degrees Celsius. We'll just use that as our starting density of air for the outside air, not inside the hot air balloon. So we'll just say that's at 20 degrees Celsius, and the mix of nitrogen and oxygen that we had before. All right, so we'll use that for the density of the air that the balloon is floating in, not the air inside the balloon. Okay, so we need to kind of take a step back to Bernoulli and buoyant forces and things like that. But remember, the buoyant force is equal to rho v g, where these rho and v are properties. Before we were talking about it in water, we would say rho of water and v of water, but this is the fluid, rho of the water of the fluid displaced, v of the fluid displaced. So in this case, it's not floating in water, it's floating in air, and so we're going to use rho and v for air. Okay, and so, and we'll just, again, it's kind of an assumption, but we'll say that V air is just going to be the volume of the balloon when it's blown up. So we'll just use that as VB, and that was a 300 cubic meters number. All right. And so we can calculate the buoyant force then as B is going to be this density of the air that's displaced, 1.20 kilogram per cubic meter, and then times the volume of air, 300 cubic meters, and then G, 9.81 meters per second squared. So we're going to end up with newtons, which is a good thing. Kilogram meters per second squared, and 1.2 and 300 times 9.81. We get 3532 newtons. All right, so that's the buoyant force that this balloon and this air can produce, right? So this is what the air has to, the ability the air has to push up on this balloon when that much on a balloon of that much volume. Okay, so the balloon then and the contents and everything need to be lighter, smaller number of newtons than this is, right? So we would say the buoyant force needs to be bigger than the weight of the balloon plus the weight of the hot air. Right, and so it's the weight of the hot air that's pushing away the normal temperature air needs to be a lot less so that it floats, right? Floats on air. And okay, so we've got buoyant force, the weight of the balloon. I think I call it VB and MB. So the weight of the balloon is just going to be mass of the balloon times gravity. And we had the mass, this is the balloon, the contents, all of the stuff before the balloon is blown up, right? So just the kind of the load. So that's 200 kilograms times G. And so the weight of the load kind of thing is 200 times 9.81 equals 1962 newtons. Okay, so this is, then we can rearrange this to get that. So this is what I'm calling B. WB. And so we've got B, which is 3532, needs to be greater than the weight of the balloon, 1962, plus the weight of the hot air. Okay, and so rearrange or subtract 1962 from both sides, and so we can get 3532 minus 1962. So 1570 is greater than the weight of the hot air. So if we set the weight of the hot air equal to 1570, that's the just starting to float point. All right, so we can say we're going to maybe just say this is equal to, just to get a number or an equals kind of equation instead of having to do greater inequalities all the time. And we're going to remember that mass, let's just call it mass of H for hot air, or HA, I guess, times gravity. Weight is mass times gravity. All right, so we've got mass of hot air then is going to be the weight divided by G, 1570 divided by 9.81. 160 kilograms mass of the hot air. All right, so keep moving things up here. Okay, so how can we figure out, we're trying to go for the temperature. We've got the mass of the hot air. So what can we do with that? So let's go back to our equation. We've got PV equals nRT. All right. So we've got volume of the balloon, volume of the hot air, right? We got R. We're looking for T. All right. So we need N and we need P. So the pressure-wise, the balloon, you know, it's an open thing, so it's got pressure on the outside, which is, you know, we've said it's 1 atmosphere, which is 101.3 kilopascals, but it's open inside here as well, so it's going to have the same pressure all over. So we can say P is just the same, 101.3 kilopascals, right? Pressure inside and out. It's not a sealed up balloon, you know, it's open, so that the pressure difference can be balanced out. So we've got pressure, so we need N, and we can solve for T. So let's just rearrange this for T for future use. We've got PV, and then divide through by N and R. But what is N? All right, so let's figure it out. So N is a number of moles, and number of moles, we have our formula way back somewhere that gave us our molar mass of air, and so for our special mix of air, and so it will be the mass we have of hot air divided by how much mass there is in 1 mole of air. All right, and so we've got 160 kilograms divided by our calculation earlier. We had the mass of air, molar mass of air is 0.02884 kilograms per mole. 0.02884 kilograms per mole. So the kilograms are going to cancel. We got 1 over moles in the bottom, so it's going to be brought to the top to be moles. So our units are working out, which is good. So 160 divided by 0.02884 gives us 5.548 times 10 to the third moles. Okay. So we're ready to get temperature. So the temperature then is PV over NR. P, 101.3 times 10 to the third pascals, standard unit, good. V was given before as 300 cubic meters, so that's good. And N we just got 5.548 10 to the third moles. And R 8.314 joules per mole Kelvin. Alright, so all that cancels out to give us temperature in Kelvin. So let's just put some numbers in. 101.3. I'm going to just cancel my 10 to the third so I don't have to put those in because there's one on the top and one on the bottom. It's in parentheses here. So I get a pretty high number, 658.8 Kelvin. So if we want to get to Celsius, we're going to take Kelvin minus 273.15. So let's subtract. Still a pretty big number, 385.7 degrees Celsius. And let's go all the way to Fahrenheit. So if we want Fahrenheit, we're going to do 9/5 of Celsius plus 32 degrees. So 9/5 of 385.7 plus 32. Okay. 726 degrees Fahrenheit, which sounds like probably hotter than a balloon could stand. And so maybe my balloon needs to be bigger or something is not quite right. So it seems like very hot. I don't think they're actually that hot. I looked up a little bit and I thought it said that it was usually around 300 degrees Fahrenheit. So got some approximations in here that are not quite right. Maybe my balloon is too small or something else is a little off. But hopefully you get the idea of how to use the ideal gas law, how to rearrange things and do the calculations to get the unit conversions right. Okay. Let's see. So, oh, I forgot to give you equations at the beginning of the video. So I guess we'll go there now. So let's look at some equations here. Alright, so we're going to look at a little bit different version of the ideal gas law. So this is still the ideal gas law, but we're going to have it with a new constant, which is actually two new constants. So we're going to, instead of having n as a constant, or n as a variable and r as a constant, we're going to have n, which is a number of atoms related to the number of moles we had before, and k, which is called Boltzmann's constant. Let me see if I can spell this thing. Boltzmann with two n's at the end, constant, and it's equal to it's equal to, where to go, 1.384 10 to the negative 23 joules per Kelvin. All right, so that's a good thing to have on your equation sheet. And then one other, actually two more equations that would be good to add are kinetic energy average. So talking about the kinetic energy of a gas, of the molecules of a gas, looking at it in terms of the Boltzmann constant is 3/2 K, which is Boltzmann constant, times temperature. So this is interesting, is saying that the kinetic energy is directly proportional to the temperature. So hotter things have a higher kinetic energy, internal kinetic energy of the gas, and it's a linear kind of a relationship, right? So it's just a constant times the temperature. Of course, temperature in Kelvin gives us that relationship. So to get, I'm not going to go through the whole derivation or the approximations and the assumptions that we make to get that. Those are in your book, so if you're interested in that, go ahead and read them in your book. But for now, let's just make sure you know how to use this equation. Similar argument for velocity. So we're going to do what's called the RMS velocity. RMS means square root of the mean of the square. All right, so we're going to take the velocity squared, take its average, and then take the square root of that. So we're looking at the velocity of a whole bunch of atoms, right? So we've got to think of a container of atoms, and they're bouncing around. Some of them are going faster than others, some are going slower, of course. And so we're taking kind of an average, or root mean square is another, not straight average, but it's a way of looking at kind of an averaged velocity for a bunch of velocities put together. All right, so VRMS is the root mean square velocity, and basically you can think of it as a kind of an average velocity of all the little molecules bouncing around in a gas. All right, so we have two different versions, or two different ways to look at this. We can look at it in terms of our R constant we had before, 3RT over the atomic mass, or we can look at it in terms of this new Boltzmann constant we were talking about, 3kT over the actual mass. All right, so depending on the problem you're looking at, you can pick which version of the velocity equation you want to use, looking at what you know and what you need. Okay, so those are the equations. I think those are the only ones, yeah, that I meant to put at the beginning of the lecture, but I forgot. So here they are. Add these to your equation sheet for this next test. All right, let's just take a step back and see how we got to this new ideal gas law. It's not really a new ideal gas law. The same ideal gas law, just rearranged. So we had before PV equals nRT, right? But we had also an equation for N, number of moles, right, is the number of atoms we had divided by Avogadro's number, right? And so we can plug that in for N. So we get PV equals capital N over Avogadro's number times RT. All right, so now we're getting close. We're kind of trying to go to this. So we got our N in there. And so then the next thing is just to say, well, just kind of factor it out a little bit or rearrange. So you've got N. Let's bring this N sub A dividing. It's dividing everything. So we can just rearrange the way we write it to be dividing R divided by N sub A. And that's what we're going to call, or that is Boltzmann's constant. So K is R over N sub A. Again, R was a constant. N sub A is a constant. And so K is just the new constant. R was 8.314 joules per mole Kelvin, and N sub A is Avogadro's number, 6.022, 10 to the 23rd atoms per mole, and that's how we come about to get our K, which was the 1.384 joules per Kelvin. Okay. Avogadro's number is really a number, so the atoms is just to help you remember what we're talking about, number of what, but it's the number of atoms. All right, so that's where Boltzmann constant comes from, and that's where this new arrangement, I guess we can call it, of the ideal gas law comes from. Okay. And so just looking at these equations, we said we can see then the relationship between temperature and energy, and also temperature and speed, right? And so the speed of the molecules, the higher the temperature, the faster the molecules are moving, right? The heavier the mass of the molecules, or the heavier, the mass per molecule, looking at this one, we can see that easier where the atomic mass is a measure of how heavy one molecule is. If the molecules are heavier, what happens? For the same everything else, the velocity is going to be smaller, right? Dividing by a bigger number means this whole fraction is going to be smaller, so the square root is going to be smaller, so a slower speed. So hopefully that makes sense. Hotter things move faster, and heavier things move slower. Okay. Let's see. I think we have an example here. Okay, so we're running out of paper. Let me steal some paper. Some new supply here. So let's look at the kinetic energy of gas. So let's just say we have gas, probably air, but let's find the kinetic energy of some gas molecules. And the temperature is 20 degrees C. And are we going to assume anything else? I think we'll go with that. All right, so just looking for the kinetic energy, and this is the average kinetic energy, right? We've got a whole bunch of molecules moving, and so the average. And so we're going to use our new formula. Kinetic energy was 3/2 kT. So pretty straightforward here. So we got 3/2, we got K, so 1.384. Whoops, I lost my, boy, I didn't do good writing here. So Avogadro, 10 to the 23, and so this one has 10 to the negative 23 in it. Boy, sorry about that. Lost a few things there. Got too ahead of myself. So times 10 to the negative 23 joules per Kelvin. And that reminds us, Kelvin reminds us, okay, temperature needs to be in Kelvin. So our temperature sub Kelvin, then add 273.15. So 273.15. So that becomes 293.15 Kelvin. All right, so the kelvins are going to cancel, and we end up with joules, which is good because that's what energy is in. And so KE average is 3 times 3 times 293.15 divided by 2. And what happened? I lost something. 3 times. Alrighty, that looks more like it. 6.09, call it good, 10 to the negative 21 joules. Alright, so very low energy, but it's energy of molecules, so we wouldn't expect it to be a huge number. Alright, and then we also want to look at some speeds, but remember the speed, VRMS, we had two formulas. Where'd they go? We got either the square root of 3 RT over MA or square root of 3 KT over M, but these both depend on the mass of the thing. So we need to know kind of what molecules we're talking about. So let's just think that it's air, and let's look at the oxygen in the air and see how fast the oxygen molecules will be moving in this air, under this air, as part of this gas we were talking about that has this kinetic energy, or these conditions, this temperature. And so in this case then, VRMS for the oxygen, let's use this one because we can get the molar mass of oxygen, or we can figure out what it is. So it's 3 times R, let's just write it out, 3RT over MA. And so we got the square root of 3. R was 8.314. Joule moles per Kelvin, joules per mole Kelvin. And T we just found is 293.15 Kelvin. And then the molar mass of oxygen we talked about before, each one is 16. Together they are 32 grams per mole. So let's get it into kilograms. So 0.032 kilograms per mole. Alrighty. And so we got moles, we got kelvins, we got joules and kilograms and things that'll cancel out, but we've got everything in our standard units, so we should be able to get velocity then in meters per second. And so let's put those numbers in. So we got square root of 3 times 8.314 times 293.15 divided by 0.023. Okay, so we got 478 meters per second. So those little oxygen molecules are moving fast. All right, but I think that actually makes sense for tiny little particles. All right, let's just go ahead and look at nitrogen as well. All right, so say some of the other molecules are nitrogen, same kind of thing. VRMS for nitrogen, 3R T, all the same. Only difference is the molar mass of nitrogen is 28 instead, 2 14s, and so 0.028 kilograms per mole. All right, so assuming we got all of our units still straight, let's do that. 3 times 8.314 times 3.15 divided by 0.028 instead. And we get a new velocity. It's what do we expect? All right, everything is the same except for the mass is smaller. So dividing by something smaller means we should have a faster speed, which we do with 511 meters per second for the nitrogen. Okay, so lighter things move faster with the same amount of energy. Think of each little molecule having a 1/2 mv squared kind of thing. And so if it's got a smaller m for the same Ke, then it's going to have a bigger v squared, right? To match up to have the Ke be the same. Okay, so I think that's all we have for today. Let's see, what should be the exit ticket? I wonder how long this video is. Anyway, check in Campus Web. I'll put the exit ticket in Campus Web and let you know what to upload there. So I'm just going to close this video here.